some about the cultural backdrop, how science fiction pervades our media, movies, TV shows, the web, and of course, science fiction always makes the assumption that there are aliens everywhere in the galaxy, and that we will be at some point in the future interacting with them. We have government agencies like NASA, which have turned the search for alien life into a business model. For example, one of the examples I gave was an interview with the International Space Station crew that was done on the Discovery Channel in 2017, where all of the crew members basically talked about how inevitable it was that we would find life out there because there are just so many stars. We observed that Americans believe that there's intelligent life on other planets. We live in a culture where 65% of our friends and neighbors, children and parents, believe that 65% believe that there is intelligent life on other planets, and 49% of Americans believe that UFOs are of alien origin. So the pervading mindset is that alien extraterrestrials exist. We talked last time about the discovery of exoplanets. Exoplanets are planets that are outside of our solar system. They're around other stars. And there's really been an explosion recently in the discovery of exoplanets. It really started with the Kepler Space Telescope when it was launched. And when I wrote this slide, I'm sure there are more now, there were 4,500 planets had been discovered, around 3,000 stars, which suggests that that's more than one per star. That suggests that there are at least 400 billion planets in the Milky Way, since some estimates are there are 400 billion stars in the Milky Way. It seems like every star we look at closely ends up having a planet around it. Most of these were discovered through the mechanism of watching for variations in light coming from a star. When a planet passes in front of it, it's orbiting it, you get this little dip in the light that's coming from it. And this method accounts for the great majority, 75% of the detections so far. There are other means to detect it, and including very important with the James Webb having been launched, the James Webb Space Telescope recently launched. It will be possible to directly image for the first time on tens of thousands of local stars. We'll be able to directly image planets that are orbiting them. That'll be potentially a breakthrough in looking for exoplanets and understanding their nature. The James Webb will also have the ability to analyze the atmosphere of these planets to look for traces of biological activity in the atmospheres. I observed that the amount of effort and taxpayer dollars going into exoplanet detection is huge. I mean, we are talking about tens of billions of dollars being spent every year by NASA on this, your taxpayer dollar at work. So the original one was Kepler. Then there's the transiting exoplanet survey satellite, whose only mission is to look for exoplanets. And Kepler has been retired, but TESS is still up there. And then very recently, the James Webb Space Telescope was launched. It was launched in December of last year. So we now have a total of 3 satellites up there, which at some point have to look for exoplanets, 2 of which are still, are currently active. We talked about some of the assumptions behind intelligent alien life. One is that one observation has been made is organic chemicals appear to be ubiquitous in the universe. And since we have found organic chemicals in many places. Certainly, they've been found on meteorites. They've been found on an asteroid. They've been found in a comet. And they have been observed in one exoplanet atmosphere at this point. So organic chemicals appear to be everywhere. And there's the hypothesis then that if there's opulent production of organic chemicals throughout the universe, and then the further assumption is through some unknown process that leads to bacterial life really everywhere. That the green scum is everywhere, that there's a planet in the habitable zone of its star. Another key assumption is that, and we're going to come back to this one later tonight, so this is a really important one. Another key assumption is that once life starts on a planet, intelligent life is inevitable. If you have bacteria, evolution will take over and you will end up with Beethoven. And the process is organic chemicals to simple single cell organisms, which are referred to sometimes as prokaryotes, which literally means without actually it's eukaryotes, means with a nucleus. Prokaryotes are without a nucleus. The prokaryotes dominated, were the only life form we had on Earth for the first 2+ billion years of life on the Earth. And then the eukaryotes arose suddenly about sometime between 1.5 and 2 billion years ago. Once you get eukaryotes with a nucleus, it is possible to develop multi-cell organisms, then plants, then animals, and then intelligent civilizations. And the assumption in the SETI community is that this process is inevitable. Another assumption is that the Earth is mediocre. Aristotle and the Bible put Earth in the center of the universe, but since Copernicus put the sun at the center of the solar system, Earth has been trivialized, and there's even a name for this. It's the principle of mediocrity. And you will read journal articles about astrophysics and astronomy, and sometimes the writers will say, we ascribe to the principle of mediocrity, meaning there's nothing special about the Earth. It's completely normal in every way. There's, I think, a quote that from Carl Sagan, who are we? We finally live on an insignificant planet of a humdrum star lost in a galaxy, tucked away in some forgotten corner of a universe in which there are far more galaxies than people. Then another great quote is Stephen Hawking's in a 1995 TV interview. The human race is just a chemical scum on a moderate-sized planet orbiting around a very average star in the outer suburb of one of 100 billion galaxies. We are so insignificant, I can't believe the whole universe exists for our benefit. So the principle of mediocrity, that we're just this tiny little scrap of dust, and that's it. So these are the arguments then for extraterrestrial civilizations. There are 400 billion stars, most of them are planets. Organic chemicals are ubiquitous. Life forms whenever organic chemicals are found. Intelligent life develops inevitably from primitive life. There's nothing special about the Earth, and our experience can be a guide to what happens everywhere. So the aliens have to be out there. They just have to. Then we went into the sort of history of SETI, going all the way back to my personal favorite example. In 1924, a National Radio Silence Day was promoted when Mars entered Earth opposition, and a radio camera was used to listen from signals from Mars. But then there's the Frank Drake and the famous Drake equation. He created it to have an agenda for a meeting he was hosting in 1961. And the Drake equation has really come to dominate the modern discussion around whether or not there are intelligent extraterrestrial civilizations. At that original 1961 meeting, the group estimated there were between 1,000 and 100 million intelligent civilizations in the Milky Way. And Frank Drake, not too long ago, 2 or 3 years ago, was quoted as saying he thought there was maybe 100,000 was his current estimate. Here's the Drake equation. It's just to show you the importance of it. This is from a page on nasa.gov. And so basically you take the number of technologically advanced civilizations is equal to the rate of formation of stars in the galaxy, which we're going to multiply by L at the end, which is the length of time such civilizations exist. And you take the two of those and you sort of have the number of stars that we're working with today that might have an intelligent civilization. And then you multiply those by the fraction of those stars with planetary systems, the number of planets per solar system, the fraction of suitable planets on which life actually appears, the fraction of life-bearing planets on which intelligent life emerges, the fraction of civilizations then that develop a technology that we could, a radio technology that we could detect. And you can fill in your favorite assumptions on these, and you can calculate the number of civilizations that are out there in the Milky Way galaxy right now. There's a website which I actually went to, and we played around with it. I have now converted this to a spreadsheet, so we can just sort of do it. But you can say, can you all see this? I can make it bigger. View, zoom. Let's make it 200%. There we go. So you can. We know that the number of stars in the Milky Way galaxy formed every year is 4. You can then start plugging in numbers. 90% have solar systems. That seems like maybe a reasonable guess based on the exoplanets that are out there. Might be a little high. Average number of Earth-like planets per solar system. Well, we have 2, maybe, arguably, in our solar system. We have Mars and Earth. So let's use that. Percentage of Earth-like planets where life forms. Again, these are these optimistic assumptions. The percentage of life-bearing planets where intelligence evolves, the percentage of intelligent species that produce radio communications, and then let's say people that a lifetime of a communicating civilization is 100,000 years. This turns out to be the key assumption, by the way. In this case, that we go as 525,000 communicating civilizations. You know, if you wanted to come in here and make that 1, you could certainly do it. You could say there's actually an estimate now, the percentage of Earth-like planets when it forms, and it's 50%. Was a recent estimate I read. And then, you know, you're getting down to more like 100,000. And this is probably how Drake is saying right now, that there are 100,000 communicating technologically advanced alien civilizations in the Milky Way at this time. There's a URL in the presentation, which I'm going to share this presentation, and Dave will be able to distribute it. And it's sort of fun to play with. Maybe I'll attach the spreadsheet too. So we talked about Drake blasting a signal off to a star that's 22,000, a star cluster 22,000 light years away. And he even included a little map so that the aliens could find us right here quite easily. Hopefully they won't come with birds of prey. We talked about the SETI Institute, 80 scientists, guided by the astrobiology roadmap, chartered by the Drake equation, funded largely by NASA in terms of its annual budget, which is NASA gives them around $23 million a year. It's run by this woman named Jill Tarter, who is one of the most, was run by her until recently, one of the most influential women in astronomy, and with all kinds of accolades and positions of influence and power. For example, the nominating committee for the American Astronomical Society. How's that for a powerful position? Disagree with her and you can't join the professional society. She is one of the strongest proponents of the fact that SETI, search for extraterrestrial intelligence, will succeed, and it's a worthwhile expenditure of money and taxpayer dollars. Today, there are many different organizations looking for alien intelligence, including the SETI Institute, Curtin University in Australia, searching the southern sky. China is getting into it. There is a currently sanctioned Russian billionaire, Yuri Milner, who is funding a project called Breakthrough Listen, which is spending $100 million on looking for extraterrestrial intelligence. So far, they've found basically zero, except for a wow signal, which was in 1977, and it was never repeated. And most, even the people who found it at this point, believe it was likely just a false signal. But so far, with this enormous expenditure, and really a lot of stars have been looked at. 60 million in Breakthrough Listen have been looked at, and 1 million stars in the southern sky, which is half the sky, have been looked at by Curtin University. So far, absolutely zero. Then we got into a really good discussion, spent a large amount of time on what would be the implications for Christianity if we found an alien civilization. In a recent survey by Ted Peters, maybe 10 years ago, I guess, 69% of those people who identify themselves as non-religious thought the discovery would cause a crisis for world religion. And we went back sort of through the history of people thinking about this problem. Jill Tarter, that very powerful woman that I described a few minutes ago, she's absolutely convinced that it will be there'll be a meltdown in Christian faith and the faith of other human religions if we were to contact an extraterrestrial intelligence. Her basically argument is if they are likely to be thousands or hundreds of thousands or even millions of years older than us, and that whatever they believe about God will be so compelling, it will be based on so much knowledge and so much history that would have been successful because they will not have destroyed themselves in those extra millions of years, that it will be so unbelievably compelling that we will all convert to whatever their religion is. She thinks that their religion will be atheism. And that we will all become atheists when we contact an alien. But she says if they're not atheist, whatever their belief is, we will all adopt it. Then we went in and we discussed what were some of the tenets of Christianity and what would be the implications if we were to contact extraterrestrial intelligence. Being created in the image of God, for example. That might be hard if the aliens have 5 eyes and 8 tentacles to sort of cope with or understand. There's the issue, a big issue, does original sin apply to extraterrestrials? Does the fall of Adam also apply to extraterrestrials? Or do they have to have their own fall that is somehow in addition to Adam? What are we to think of the incarnation of God in the form of Jesus, if there are other intelligent beings on other planets? Does Jesus have to be incarnated there too? Sort of a traveling incarnation, sort of like a traveling salesman. Doesn't feel right somehow. And a key one, did Jesus die for their sins too? And this has been being debated for a very long time by Christian philosophers. We talked about how rank and file Christians actually don't feel like they'll be that big of a crisis. That survey that Ted Peters did, and it turned out that most of the people who identified themselves as religious thought it would be no threat to their personal beliefs. So we're finding answers to these questions, or at least I think we are. I think we finished with this slide, which was C.S. Lewis on these questions in his 1958 essay, Religion and Rocketry. He reduced the religious issues related to aliens to a series of questions. And these were the ones: if aliens exist, do they have rational souls? Which he explained to mean, are they concerned with values? A tiger eating an antelope he's not concerned with whether or not the tiger is not concerned with whether or not it's a right or wrong action. You don't really, as human beings, uniquely consider the question of our actions right or wrong. And so his first question is, where are the aliens on this? Another question is, are they guilty of sin, or did they live in perfect harmony with God's will? Did they fall? Maybe they didn't. And if they did, have they been denied redemption by the incarnation and passion of Christ on this earth? And do they, and also, and do not have a local redemption from Christ? And, we don't really know the answers to these questions. And if yes to all of the above, the last question is, are there other modes of redemption than we know? And his point is, we can only know this if God reveals it to us. So his conclusion was, wait to worry about these questions and until we know if they're aliens. And so this is where we left it. I'd like to pause for a moment and see if anyone would like to bring up any comments or questions or about any of this material that we covered in the first meeting. What are your thoughts on it before I go on now into the second part of the presentation, where we look at this real question of what is the true probability? How many alien civilizations might there be out there, and what is the probability we will contact them at some point? That'll be the next section. So please, everybody, join in at this time if you have any comments to make.
I'd like to know what would the position of these scientists be regarded by themselves as a faith position lacking, determinative knowledge?
Yeah, I think they would not be comfortable with that, even though it seems obvious to us, doesn't it? Faith is what is the famous quote? Faith is the hope of things not seen. And I don't think I quite got that exactly right, but I think scientists take the position that the calculation of the Drake equation implies that there are many civilizations currently in existence in the universe, particularly if you believe in that chain of assumptions. Organic chemicals are everywhere. You get life if you have organic chemicals, all the way down to, if you get bacteria, you get Beethoven. So I think that they would view that as a reasoned position based on the evidence that they have. And they're not particularly interested in skeptically examining their assumptions.
Thank you.
Hey, David, can we go back to that slide with Drake equation? The spreadsheet.
Oh, let's do the spreadsheet. That'd be easier.
Okay, here, yeah.
I made it a little too big.
That's fine.
But
that's fine. So I do have a lot of questions about this assumption, but the major one is number 9, percentage of life of a planet where intelligence involved. They put it at 90%, which is way, way too high. We have absolutely no evidence of that. I have all these assumptions, doubt on all these assumptions all the way from beginning to the end too. The assumption about organic chemistry is everywhere in the universe. What is the percentage of asteroids that come down that we discover there are organic chemistry there? I mean, we cannot even find organic chemistry in Mars. So I don't know where do they get those assumptions from. But the biggest one for me is percentage of life-bearing planet where intelligence evolved. Oh, that's I'll put it at almost zero. I don't know. Anyway,
we're going to hold these thoughts because we're going to really cover some of this in the upcoming slides. We're going to attack these assumptions.
Yeah. Let me also mention, I never liked the Drake equation because it adds this scientific air to things. And it's basically, you make a list of all the stuff you don't know, and then you multiply the probabilities.
Yeah.
Okay. Like what's scientific about it? Like, yeah, this is all the stuff I don't know. And then you just multiply it together.
So I'm wondering why
This
they
number is scientific. That's the end of the science.
So I'm wondering why we've got the average number of Earth-like planets per solar system to be one. They've really not found. So I think is that how he really defined it, or is it the number of planets that are capable of hosting life? Because right now we've found like 0 or 1 or 2 out of 4,000.
Well, I don't think it's quite
most
that
of everything
bad.
we find are, of course, so far are the big Jupiters. We're starting to find some of the Earth-sized planets, but
This is also a lot of problem here in this assumption. He says Earth-like planet. Okay, so Earth-like in terms of rocky Earth, rocky planet, or is that the only thing they're looking for? Or are they talking about 70% water cover surface? You got a climate, you got a tectonic planet, you got a magnetic field shield. I mean, have we found those? I don't think so. And that's my problem with all these assumptions.
On this one small point, there is a current estimate that 50% of the stars that we have found an exoplanet around have a rocky planet in the habitable zone. So there would be a basis for putting 0.5 there based on that sample. Now, it doesn't address all the other things, David, that you mentioned, but that would be a number that someone could stand up and defend. That rocky planets in the habitable zone of the stars, maybe half of the stars we've examined closely enough to have planets that would meet that criteria. Now, that's not exactly Earth-like. That's rocky planets in the habitable zone. So in our solar system, that would include Mars, which we know is devoid of life. But that now takes us to the next assumption, where basically half of the planets in our rocky planets in our habitable zone have life on them. So that would be another, it's sample size of 1, confidence interval would be a division of n-1, which would be 0, which would blow up the confidence interval. But yeah, we're gonna drill into all of these things. Maybe I should get back and get us started on that. Are there any other comments other than attacking the Drake equation, which I'm going to really do a lot of in the next section?
Yeah, I guess I have one comment, and that is that the RTB scholars have gone through all the requirements for life on this planet, and they have over 1,000 requirements for intelligent life to exist. And the probabilities are so huge that it almost that the number of planets that have the same qualities as the Earth are almost 0. And these are things that are quantifiable and measurable.
Yeah.
There's several books.
I would
go ahead.
I'm going to quote Hugh Ross here in a few minutes and his book Improbable Planet. So if there's more than in that book, I would really love to have access to it. And maybe afterwards, Paul, you could drop me a line. I'm David at northernlight.com. You probably saw me on the invitations. And I would love to know more about the rest of the factors that aren't covered in the Hugh Ross book.
Okay,
so
sure.
I'm going to talk about that book in a few minutes.
It's like the assumption is dirt plus life, dirt plus water equals life. That's the formula they're operating under.
Yep. By some unknown and mysterious process that no one can model. Okay, so everybody has probably heard about the Fermi Paradox. In 1950, Enrico Fermi, who was the creator of the first nuclear reactor, sort of one of the giants in physics, wondered after a lunchtime conversation with Edward Teller, who was also one of the giants in physics, he wondered about the presumption of numerous highly advanced civilizations. That was the discussion topic at lunch. They were in 1950. And this was, 11 years before the Drake equation was even expressed. So his question that he came up with is if there are so many aliens out there who are so advanced, where are they? Why haven't they visited us? And there's sort of three classical answers to this. One is we're the only intelligent civilization. The second one is we're the first and therefore the most advanced. And the last one is the barriers, the technological barriers are just too high. They're too immense to be overcome ever. Now, I went on a quest to find recent estimates to the Drake equation because since 1961, we've learned a tremendous amount about the requirements for life and how solar systems form and how the galaxy has evolved. And the best recent paper I could find was the Astrobiological Copernican Weak and Strong Limits for Intelligent Life, published in a peer-reviewed journal by Tom Westby and Christopher Consolis from the University of Nottingham. And they refer to a communicating extraterrestrial intelligence as a SETI with a C instead of with S, which of course means search for extraterrestrial. So we're going to talk about SETI here, but when I say the word, I mean CETI most often. And they made adjustments to the Drake equation. They adjusted, one of the things they did was they adjusted for the metallic content of stars. And they looked at the population of stars and how old they had to be to have high metal content, since high metal content would be required to have anything other than gas giants. And so they did that. And then they adjusted for the stellar lifetime, which is part of the metallic content of the star, because you have to have a third generation star to have a high metal content. Also, for what it's worth, I wrote both Tom Westby and Chris Consolis about their paper, and Tom Westby helped me with some of the calculations I'm going to show you. Really nice guy and quite interested in this topic. So they basically modeled three different situations. One was SETI lasts for 100 years. A communicating extraterrestrial intelligence lasts for 2,000 years before they stop communicating or blow themselves up or something, have a natural disaster, or an asteroid wipes them out. Or SETI lasts for 1 million years. And using the Drake equation, but adjusted for those other factors. In the first case, they came up with there are 36 current SETIs in our galaxy was their estimate. But one of the interesting things they did was they calculated how far away the nearest one would be expected to be. And in the first case, 17,000 light years away. And there are approximately 2 billion stars in that volume of space around us. Now, the 100 years is one that people like to use because we've been communicating for 100 years. We haven't blown ourselves up yet. And we've had radio communications for roughly 100 years. So it's safe to say that at least 100 years. Now, in the second case, 2,000 years, if the SETI lasts that long, they came up with 710 communicating extraterrestrial intelligence. The nearest one would be approximately 4,000 light years away. And the number of stars in that volume of space is around 100 million. Now, 100 million is starting to get order of magnitude what we've looked at, right? Curtin University looked at 1 million. Breakthrough Listen is planning to look at 60 million stars. You know, it's becoming manageable, perhaps, to look for things. And then in the case of SETI lasts for 1 million years, there'd be 355,000. Remember, Frank Drake thinks 100,000. There would be 170 light years away, and there'd be 68,000 stars in that volume of space around the Earth. Now, there's an interesting, and from the viewpoint of SETI, Search for Extraterrestrial Intelligence, these numbers are quite depressing for the following reason. Communication is impossible in the first two rows because the round-trip radio signal exceeds SETI's lifetime. If SETI lasts for 100 years or 2,000 years, and it takes and the nearest one is 17,000 or 4,000 light years away, the round trip, which would be 34,000 light years in the first row, or 8,000 light years in the second row, exceeds the lifetime of the civilization you're trying to communicate with. So if either of these applied, it would be impossible for us to have a communication. We might discover after they're gone that they existed, but we would never be able to communicate with them. The next part, we're going to talk about the issue of M-dwarf stars in just a moment. But if you look at the 68,000 there, about 14,000 of them would not be M-dwarfs. And M-dwarfs are probably uninhabitable by any life at all, or even, and especially advanced technological civilizations. So in the case of SETI lasts for 1 million years, which gives you 355,000 potential communicating civilizations out there. In the we look around us, 14,000 candidates would be where you would start, and you should find one in those 14,000. We looked at 1 million with Curtin University in the southern sky, and didn't find anything. SETI in the northern sky has looked at many thousands of stars. Breakthrough Listen has looked at some number of millions of stars, and we haven't found anything. So while this row might give you some encouragement if you're a pro SETI enthusiast, in fact, it has some dire implications for the search for extraterrestrial intelligence. Westby and Consolis concluded the following. Spread uniformly throughout the galaxy, this would imply the nearest communicating extraterrestrial intelligence is at a distance likely far surpassing our ability to detect it for the foreseeable future and making interstellar communication impossible. So this is the most recent update, the conclusion of the authors to the Drake equation. This is the most recent update to the Drake equation, considering these additional factors of metallic content of the star and the stellar lifetime, which the Drake equation ignored. Now, a key conclusion by Weber and Consolis in recalculating the Drake equation outcomes is that the star census analysis implies most SETIs in the galaxies will be found around M-dwarf stars. If M-dwarf stars can support life, and if they can't, the number of SETIs plunges by over 80%. And you can see the quote here: "It's spread uniformly near SETI, blah, blah, blah. Furthermore, the likely," here, the second part is the new part. "Furthermore, the likelihood that the host stars of this life are solar-type stars is extremely small, sun-like stars like Sol, and most would have to be M-dwarfs, which may not be stable enough to host life over long time scales." So this is a picture of an M-dwarf star on the left. Happens to be Proxima Centauri, which is the closest star to the Earth. It's just under 5 light years away. Actually, it might be 4.22 if I remember, something like that. And it is an M-dwarf. And M-dwarf stars are small and cool, and they have extremely long lifetimes, 10 trillion years. So our star will last about 5 billion years, where before the space around it will become uninhabitable. We are at 4.5 billion of those 5 billion years right now. But if M-dwarfs can last for 10 trillion years, so that's a long time. Now, this was referenced in their paper, but not extensively discussed by Weber and Consolis. M-dwarf stars are thought by many to be hostile to even primitive life. This is a 2-scale drawing of an Earth-sized planet orbiting very close in the habitable zone of an M-dwarf star. And here's the key: it has to be so close to the star to be in the habitable zone from a temperature viewpoint that it would be tidally locked, which would mean that it would always face the same face of the planet would always be toward the sun. And what that means is one side would become raging hot, too hot for organic chemistry, and the other side would be deeply frozen, too cold for organic chemistry. And the heat and the cold, neither one, can support any model of life, even primitive life, even the green scum level of life, much less advanced technological civilization. The other thing is that M dwarfs have solar flares from time to time, and that those solar flares reach further out than an orbiting planet in its habitable zone would orbit. And so from time to time, the solar flares would sterilize both sides of the planet, the part facing the star and away. So by ignoring the issue of M dwarf stars, you immediately, the Drake equation immediately sort of tumbles to rubble. And again, this most recent update I could find, Weber and Consolis do comment that this is a very serious issue for the search for extraterrestrial intelligence. I communicated, as I told you, with Weber, and I said, boy, this must be very discouraging for the SETI with an S, the SETI community. And he said, yes, it is. It's very discouraging, but it's not part of the public debate around should we be giving tens of millions of dollars to the SETI Institute and launching satellites for billions of dollars to keep the search going. So this now brings us to the rare earth hypothesis. Rare Earth, Why Complex Life is Uncommon in the Universe, was written by Peter Ward and Donald Brownlee in 2000, and it mounts an all-out attack, really, on the Drake equation. Ward is a professor of geology. Brownlee is a professor of astronomy. They're both at the University of Washington, and they lay out a case for why we may be the only intelligent civilization in the galaxy. So first, they start with, okay, there's as many as 400 billion. You see estimates of 100 billion. You see estimates of 200 to 400 billion. 400 billion is sort of the max that you ever see. Because so many of the M dwarfs, and we can't see M dwarfs beyond, if they're very far away, they have to be close to us for us to see them with telescopes, because so many are M dwarfs. That's why there's so much variance in the estimates. Most of the stars in the Milky Way we can't see. But let's take 400 billion just to give the maximum probability to extraterrestrial intelligence. So Brownlee and Ward point out globular clusters of stars are a hazardous place. They are metal poor. Solar mass stars are too large and too hot. And there are frequent stellar encounters where stars pass close enough to each other to disturb either the star and its own structure, or certainly to disrupt any orbits around any planets orbiting around them. And a very large number of stars are in the Milky Way are in clusters. The inner regions of the galaxy are there's too much going on. Too much radiated energy for life to exist, or at least for complex technological life to exist. It's not to say there's not some crystal on a rock that is reproducing in a crystalline form of green scum or something like that. But advanced technological life would be impossible in the inner regions of the galaxy, and you'd also have too many stellar encounters causing problems. They point out that the outer regions of the galaxy, most of the stars are too metal poor to form rocky planets. They're all stars that haven't gone through the right life cycle in order to have metals. You have to have a third generation star, and they are without the metal, you can't form rocky planets. And the outer regions of the galaxies, things that are in the spiral arms, are too metal poor for that. And planetary systems with hot Jupiters or gas giants in eccentric orbits would drive the inner planets into their star, eject them from the solar system. And hot Jupiters are being found commonly in these exoplanets in these stars with exoplanets that we're discovering. So those all would prevent life, a complex technological life from arising. And then they also have what they call the rare earth factors, which are required to support the evolution of complex life. And just running through this really quickly, the right mass of the star, the right age of the star, 4.5 billion years is sort of a sweet spot in terms of the age of the star. Stable planetary orbits, the right planetary mass to retain atmosphere, need a molten core to shield us from the solar wind so our atmosphere doesn't get stripped away, and also to have plate tectonics, which brings the minerals up to the top where we can mine them and build our complex technological civilization on them. You need a Jupiter-like neighbor with a stable orbit. You need plate tectonics to build up landmass, enhance biotic diversity, and enable the magnetic field, which is really more the core point, I think. But here's a really big one. You need a large moon with the right distance to stabilize the tilt of the Earth. The tilt is really important, and Earth has an unusually large moon. And certainly, if you look at the solar system, and how many moons does Jupiter have? I forgot the number. Is it 79 or something like that? But they're all small. And even the four we can see, we talk about at Jupiter are small compared to our moon. And our moon has many benefits. It is the most important one being to stabilize the tilt of the Earth. And that tilt turns out to be quite important in terms of distributing temperature across the surface of the Earth. We have seasons that are crucial to the planet's ability to support complex technological life, things like crops that you would need for such a civilization. You need no sterilizing impacts after a certain period. We've had multiple impacts on the Earth. There's the late heavy bombardment, for example, that would have destroyed all life, but we haven't had one since life got started here. And that's sort of luck to a certain extent. You have to have the right amount of carbon, not too much, not too little. You have to have the right atmospheric properties. You have to have an evolution of oxygen at just the right time. And photosynthesis needs to be, oxygen and the development of photosynthesis need to go together. You need the right position in the galaxy, not in the center or the edge, not in the spiral arm. And you have to have a successful evolutionary pathway to complex plants and animals from single cell life. So they have all of these extra things that they bring into the equation or into the discussion. So they have something in the book they call the rare earth equation. And I've lined it up here against the Drake equation so you can see where the factors are the same and what the additional factors are. And I have relabeled some of their equation, some of their labels. For example, they have this one, but they changed it in the book on the letters, and it becomes really confusing when you try to go through it. So I have tried to make it easy to compare. So there are some things they do the same. They don't worry about the rate of star formation and then multiply it times the number of years a communicating civilization survives. They really hate this assumption. It's totally non-scientific. Pull it out of, it's almost political. Pull it out of your ear. So they just stay away from it. They don't try to do anything with that. So they substitute that product of the number of stars formed in the Milky Way, which is R times L. They dispense with that product, and they make what is actually a more favorable assumption to communicating extraterrestrial intelligence, which is the number of stars in the galaxy. So that would be 400 billion. So that's a much larger number than the product would be on the left. Then they do talk about the fraction of stars and planets, the number of planets per solar system suitable for life in the habitable zone, and the fraction of planets that develop life. They then talk about additional things, the fraction of planets that are metal rich, which would be required. You'd have a rocky planet where you could develop a technological civilization and have the kind of chemistry required to evolve complex creatures, which goes with the metal. It's not just having metal to make semiconductors out of it, it's having the biochemistry required to develop advanced organisms. And they talk about the fraction of stars in the galactic habitable zone, which is totally missing from the Drake equation, the fraction of planets where complex metazoans, which I described earlier as eukaryotes, arise, and then the fraction of a planet's lifetime where the presence of complex metazoans. And this is a really big issue to them. They have 3 chapters on the evolution of life and from single cells to complex animals and plants. And we'll talk about this more in just a moment. They mentioned in their equation the fraction of planets with a large moon. I don't know if you all remember the current hypothesis about how our moon came into existence, but there was the best idea is there was a collision between Earth and a planet almost the size of the Earth that collided at a particular angle, a particular relative velocity, and the result of that was material ripped out of the Earth to form the moon. Without that collision, you get a small moon instead of the big one that is capable of stabilizing our tilt. And if you start thinking about how probable is that, you have to have a collision at the right moment in the formation of both of the Earth. You have to have a collision at the right relative velocity. You have to have a collision with a body of the right relative size. And if you're looking for this is not fine tuning, but those parameters have to be fine tuned in order for us to have a moon which permits the kind of advanced technological civilization that we have. And so they talk a lot about that. They talk about the fraction of solar systems with a large Jupiter to protect the inner planets, and the fraction of planets with a critically low number of mass extinction events. So all of these things are then added to the equation. Now we'll in just a moment we'll go back to our spreadsheet, and I have this on a spreadsheet as well, and we'll take a look and sort of play with it. But their conclusion was, again, this is a quote from the book. Again, as any term in such an equation approaches 0, so too does the final product. How much stock can we put in such a calculation? Clearly, many of these items are known only in the sketch's detail, but as our contention that any strong signal can be perceived, even when only sparse data are available. To us, the signal is so strong that even at this time, it appears that Earth indeed may be extraordinarily rare. This is the exact opposite of the mediocrity principle. Now, I have not been able, whereas for the Drake equation, you search for the Drake equation calculator on Google and you have hits all over the place. But for the rare Earth equation, there are no NASA pages. There are no internet calculators. There's only one article that I could find from the time that references an attempt at the math. It's a well-respected writer, John Kramer, who wrote a great book on quantum mechanics, which is highly regarded. And he wrote in Analog Science Fiction and Fact magazine, the conclusion of Ward and Brownlee, which I have only been able to sketch here, is that Earth is a rare place where many random factors have conspired to create a nearly ideal state for the evolution of complex life, pulling plausible numerical estimates into the rare earth equation, which he says was not done in the book. And I was frustrated by that. I really wanted him to. Suggests that there are only a few planets with complex life per galaxy. Thus, it is possible that Earth is the only planet in our galaxy with intelligent life. I found an article which, the 20th anniversary of the book by Ramses Ramirez, who is a researcher at the University of Central Florida, has also a seat at the Tokyo Institute of Technology. His specialty is the biology of Mars, interestingly enough, the search for life on Mars. And he's a serious guy. And he wrote, when he did a review of the book 20 years later on its anniversary, an impartial evaluation of the evidence supports the premise that complex life, including animal life, might be rare throughout the cosmos. If the rare earth hypothesis is correct, a SETI search for complex, intelligent life faces unbelievably low chances for success. So with that, let's do our calculation. So here I have, this is the Drake equation. And here I have added the factors from the rare earth equation, which I should label. Do that. Nothing like writing your presentation in front of your audience. Here we go. And so this is sort of, I have made an attempt to find numbers that could be defended, and it is really hard somewhat to do that. So I have plugged some in here. The fraction of metal-rich planets, there's 0.5%. There's actually a basis of that, which is the number of sunlight planets as a percentage of the total number, sunlight stars as a percentage of total number of stars in our galaxy is 0.5%. So I took that as the fraction of metal-rich planets. The fraction of stars in the galactic habitable zone, this is a number that people do write about. Less than 1% is an estimate that I have read, so I used 1%. The fractions of planets where complex metazoans arise, I take 1%. I'm going to defend that in just a moment. That might be very high. That might be way overstated. The fraction of planets, the fraction of a planet's lifetime with the presence of complex metazoans, I took 50%. That might be wildly optimistic too. That is true on Earth. We've had complex metazoans for half of the time period where we've had life on the planet. I will discuss that in a moment. So my sample size is 1, so I took 50%. Fraction of planets with a large moon, I pulled this out of the air. I don't really know how precise the fine-tuning is for that event, but 1% seems wildly optimistic to me, and it could be easily much smaller than that. And then I come up with the fraction of solar systems with a large Jupiter. There's actually a basis for this number, which is from the exoplanets and looking at the star systems. About 20% of them that we found seem to have a large gas giant. So that number might have more. And then the fraction of planets with a critically low mass extinction events, I took 10% in this calculation. I don't really know what a good basis for a number would be. We have rounding off 10 planets and 1 planet has life, so maybe 10%. But, you know, I don't know. That's really an apple and oranges comparison. And I think one could model this looking at the number of mass extinction events we've had, which are, I think, 4. And 4.5 billion years, and if the probability is 1 every billion years, someone better than me at statistics could probably figure out a way to estimate that. But for this purposes, I took 10%. And then I used 70% for the percentage of stars that have solar systems. And that would be true in both of the case of the Drake equation and this is overlapping factor, so we want to make them equal. 0.7 in the average number of Earth-like planets per solar system, and 0.7 times 70% is 50. And that's a number based on the exoplanets that we have found so far. So those two are probably pretty good. And now the next one, the percentage of Earth-like planets where planets form. This could be wildly overstated. This is to David, to your point earlier, could be wildly overstated. I wanted to get a number similar to 100,000 here because Frank Drake believes 100,000 is the number. So I had to plug 70% into that. I mean, that might be 1%. That might be a tenth of 1%. We really don't know. But 70%, even at that and these other assumptions, you get 7, which, given the accuracy of these numbers, could easily be 1. Could easily be 1.
So,
all right. Let me pause here. We're going to talk a lot about this in a minute. So you can, if you can wait on attacking these numbers there, I will attack them for you in a minute. So go ahead.
So I have a little different approach on all of this. I think this is the Drake equation and these high number of estimates are a great apologetic tool. I wish the number was 100 million. And they find nothing.
Yeah.
So the bigger that number is, the stronger our case is. If we get that number down to 1, they're just going to say we need bigger telescopes to look at more galaxies before we can make a determination.
Well, that's a really good point, Chuck. I think the energy around the apologetics community is to make the number smaller.
Yeah.
And your point is we should be trying to make the number bigger.
We should every star, or next door star, should have formed it, and it will just make them much sooner rethink their entire assumptions. Otherwise, we can't make a telescope big enough to really disprove their assumptions.
Very good point. Very unique point too, by the way. Totally original.
There's a reason why rare earth equation is not adopted by NASA, because how do you get the funding? How do you get the people, taxpayer, to pay taxes, knowing that that is a chance? That's a problem. So it's not politically, it's not acceptable to advertise that.
Personally, I might start funding, helping to support. In the early stages, there's no gain, but once they start running it out, there's a huge gain for us.
Very interesting.
Interesting.
Any other comments before we press on? We're going to focus on this question right here in a minute.
I was going to mention, it feels a lot like marketing to me, where you're doing a business plan and you're trying to figure out how many you can sell of something. So yeah, there's like 1 billion cell phones sold every year. We could get at least 10%. Okay, so you're kind of
that's it.
Pulling numbers out of your ear to just
You start with the conclusion and then you work backwards, right? That's what we do. It's exactly that in a business plan. We're going to be $100 million in 5 years in revenue, and we're going to be worth 10 billion, and we're going to do it because of, we'll figure out some assumptions that will make it work.
So in trying to get your number up, if I would take the fraction of planets with a large moon, we're not able to really detect moons. I think on exoplanets, I think they may have on 1 or 2, but we have a case study here. We've got 8 planets and 1 has a large moon.
Yeah.
So I would set that number at 12%. Okay, now we only need another factor of 100,000.
I've already got 400 billion stars, so we can't change that.
I have one question
I
about,
went to the top.
I've got a question about what kind of information is being gathered besides finding evidence for extraterrestrial intelligence. Is anything else being gained from these searches? Any other useful information, or just cataloging stars? I mean, is there anything else?
Well,
other than-
many of these programs are what do you call, not parasitic, but they're symbiotic. So they're just sharing some of the data, like the Arecibo, when that was online, the data that was taken there was, yeah, it's used for multidisciplinary, but I don't think like the Allen array and some of those that are dedicated, they're probably more SETI than science, but some of it definitely is shared.
I hate to
So the
think,
SETI
And
scientists,
the primary goal of James Webb is not SETI. You know, it's really to look at the beginning formation of our universe, how the stars and galaxies first formed, and to answer some of the questions about inflationary theory, dark energy, and dark matter. But yes, that telescope, we will be able to image planets, so we will be able to get spectrum of exoplanets. So it can be used, you know, and to benefit the SETI research.
also, I think SETI scientists now are given a percentage of their day to work on non-SETI things because it was viewed as a detriment to their career to only work on SETI. So they're working on other stuff as well.
I also look at it as employment for graduate students. So I studied signal processing, and that was very well known. Like SETI is doing these giant FFTs, looking for some kind of sinusoidal component and all that.
Yeah, graduate students are plentiful and cheap, aren't they?
Yeah.
So, all right, let's keep going. Brantley and Ward have had a maelstrom of criticism heaped on them by the atheist scientific community that is continuing to this day, 20 years later. Frank Drake himself said the basic flaw in all these arguments is they don't allow for opportunistic nature of life, its ability to accommodate or alter itself to cope with environmental change. And that's in fact not true, and I assumed he didn't read the book. They are not opposed to the idea of green scum everywhere, and they're not opposed to the idea of other types of primitive life everywhere or in places that couldn't support green scum. What they're talking about is complex technological life, and the constraints on that are much more extreme than the constraints on green scum. Then another quote, one of the strongest influences, and this is a big deal, this really has led to some consequences. One of the strongest influences on the authors, a young University of Washington astronomer who they acknowledge in their preface, changed many of our views about planets and habitable zones, has a hidden Earth is unique agenda motivated by strong, intelligent design, religious views. They did have a lot of advice around these issues, planets, habitable zones, from a committed Christian who was on their, who's a member of their academic community, and who has, and unfortunately, Brownlee and Ward did not realize his religious beliefs, and Brownlee in particular was embarrassed when it was pointed out to him by a reporter. He basically at first said, no, it's not true, he's not. And then later when he realized that it was true, he has been personally embarrassed by it. But from a logical viewpoint, this is a classic logical error of logic. You don't attack the speaker, you attack the argument. The question is not whether or not a Christian advisor to Brownlee and Ward is a Christian. The question is whether or not the advice was correct or incorrect. And no one has attacked the science in the book. They're attacking the motivation in the book. Nowhere in the entire book does the word God appear, not once. It is nowhere there. Intelligent design doesn't appear there. The word miracle doesn't appear there, even though they talk about how rare some things are. But this has led, there has been so much criticism that's continuous. Here's a quote from Neil deGrasse Tyson, 2021, last year. This scenario is popular with religions that favor Earth as God's unique and special place in the universe. Just dismissing it with a wave of his hand and not looking at the science at all. This is a quote from a book that he released last year. It was, and I actually wrote a review of it for the ASA, the American Scientific Association. You guys may be familiar with them. They are an organization of scientists that looks at science and religion, and very, very interesting group. So anyway, but you can see here's 20 years of criticism. Brownlee wavered. He has said, well, you know, there's so many stars, there has to be life out there everywhere. And Ward sort of just as not engaged since the book was released. But Brownlee just couldn't take the criticism, and he actually wavered later on. Okay, so let's take a look at one of the key assumptions. The assumption that once life starts on a planet, intelligent life is inevitable. And here's, you know, the chain of events. Organic chemicals leads to single cell organisms that do not have a nucleus, which leads, and they evolve to complex single cell organisms, eukaryotes, which then, because of the way DNA works inside the nucleus, permits the evolution of multi-cell organisms. And then you get plants, animals, and intelligent civilizations. You start with bacteria, and you get Beethoven. So there's been a lot of research in this area in the last 20 years. And if you sort of look at the timeline, Earth was formed 4.5 billion years ago. Life starts 4 billion years ago. And these are the prokaryotes. I hope I'm pronouncing that right. Some of you who are academics are probably cringing when I pronounce it, but you can let me know if I'm getting it wrong. The prokaryotes, and then they persist for over 2 billion years and don't evolve into complex multi-cell plants, creatures, plants, or animals. They're sort of stuck. And then suddenly we get the eukaryotes appear in the fossil record at this point between 1.5 and 2 billion years ago. And they evolve. And that leads to, at some point, the Cambrian explosion, which leads to dinosaurs and finally us. And what is interesting about the arrival of the eukaryotes from analysis of the fossils is there are no intermediate steps. There are no intermediate steps between the prokaryotes and the eukaryotes. You've got 2 billion plus years of prokaryotes, and then suddenly you have eukaryotes, and there's nothing in between. Now, it's long been observed that the structure of complex cells mirrors a combination of two more primitive types of cells. And sort of the two big families of single cell organisms are archaea and bacteria. In 1967, this led a scientist named Lynn Margulis, who's a very interesting person. She was this very active feminist scientist. She was married to Carl Sagan for 7 years and had 2 children with him. She put forth the idea of endosymbiosis, proposing that eukaryotes arose when one cell ingested but did not digest another cell and incorporated it into its structure. Today, it's been established that an archaeon ingested a bacteria. So here's the archaeon. And the difference between a bacteria and an archaeon is, from my viewpoint, from a non-practitioner, is subtle. Has to do with the structure of the cell wall and the chemical composition of it. It has to do with how the mechanisms operate inside the cell. Remember, you have no nucleus. Things like production of energy are accomplished in similar but different ways. And so bacteria and archaea are differentiated by biochemical process differences and by structural differences in terms of the chemical compositions of their of the cell. So the idea is that an archaean ingested a bacteria. It happened twice, and the first step was to get mitochondria into the cell, and these evolved into animals eventually, and that a second event occurred when another bacteria that was able to engage in photosynthesis was ingested, and you got a plant cell which has both mitochondria and chloroplast in it. And if you sort of look at this from a tree viewpoint, you get the last universal common ancestor here, and it splits into bacteria and archaea. But then at some point, this bacteria gets ingested into an archaeon, and that starts the eukaryotes. And then one more time it happens, and then you end up with plants, animals, and all the other families that we have. In the meantime, the archaea never evolved into complex creatures. They're still part of the biosphere of the Earth, but they're still single cell. And the bacteria never evolved into complex creatures. They're still part of the biosphere of the Earth, and they're still simple single cell creatures. Now, there's been some evolution of the processes inside them in both cases, but they never became multi-cell. And we're talking here about the evolution of complex technological life. And over 4.5 billion years, these paths never got there. And the only one that did was when a cell and one cell ingested another, didn't digest it, but incorporated it into its energy producing processes. This has been very well supported now by genetic analysis. We can sequence DNA, and so the genetic evidence strongly supports this. The lines here are overlapping DNA between archaea, bacteria, and us. And the number and the width of the line is the number of genes that are identical between these. And you can really see that complex life is a union of the two of these. There are also other things that there's other evidence that supports endosymbiosis. Mitochondria and chloroplasts, these things that are inside that came from the bacteria inside the cell, are circular, and the prokaryotes, the bacteria and the archaea, have this circular DNA. So does mitochondria and the chloroplast. The mitochondria and the chloroplast have a double membrane, and there's a process that would produce that. And this is a really interesting one. The mitochondria and the chloroplast have 70S ribosomes. That's a measure of size, and it has to do with how fast the cell actually moves in a centrifuge. Smaller ones move faster. And so the mitochondria and the chloroplasts have inside our cells have 70S ribosomes, and bacteria and archaea have 70S ribosomes, whereas the rest of our cells have 80S ribosomes. So the 70S seems to come from these two, and there's a really good book on this by a biologist by the name of Nick Lane. Let's see, that the City University of London, and it's called The Vital Question. He has put forth the idea that modern complex life depended on an extraordinarily rare singular event. I quote from the book, "We know that complex cells arose on just one occasion in 4 billion years of evolution." He thinks one cell it happened with through a singular endosymbiosis between an archaeon and a bacterium. Life arose around 500 million years ago after the Earth's formation, perhaps 4 billion years ago, but then it got stuck at the bacterial level of complexity for more than 2 billion years, half the age of our planet. Indeed, bacteria may have remained simple in their morphology throughout 4 billion years. In stark contrast, all morphologically complex organisms, and that's referring to like body parts and organs and things like that. All of these complex life families, plants, animals, etc., descended from that singular ancestor about 1.5 to 2 billion years ago. If you're looking for an example of a miracle, I will submit this one to you. This is a really good one with good science behind it. One archaean ingested one bacteria in the history of life up into that point, billions of years, and that led to the evolution of complex life. And it suggests that it is, and how many trillions and trillions and trillions of those cells are out there, and it happened once. And that, to me, is a miraculous event. So we have our key assumption that once life starts on a planet, intelligent life is inevitable. Maybe not. Maybe the normal natural process is it gets stuck at the prokaryote level and never evolves beyond the level of green scum. And that complex life, multicell organisms, plants, animals, and civilizations, intelligent civilizations don't evolve. I think it would be quite reasonable. And again, Brownlee and Ward spent 3 chapters of their book discussing some of these things. Not quite as directed as I've been here, but now there's some more evidence to support this. There's a recent paper by Andrew Snyder-Beatty and others. Andrew Snyder-Beatty is sort of a celebrity in this area, and the paper is called "The Timing of Evolutionary Transition Suggests Intelligent Life is Rare." And what they do is they look at protein folding, and they figure out how much protein folding is required to make a particular evolutionary jump, and how many evolutionary jumps there have been between the single cells and us. And then they imagine a space with the volume of the Earth's oceans and a certain density of proteins being folded at a certain rate by the organisms that are there, and they calculate how long it should take to evolve us. And their conclusion is, together with the dispersed timing of key evolutionary transitions, and they're doing a Bayesian analysis, so they're referring to plausible priors here, one can conclude that the expected transition times likely exceed the lifetime of Earth, perhaps by many orders of magnitude. In turn, this suggests that intelligent life is likely to be exceptionally rare. Another comment they made is the model provides a number of other testable predictions, including that M dwarf stars are uninhabitable because the rate of protein folding in those stars would be, in planets around those stars, would be inadequate to develop life. Then we have Hugh Ross in his book, An Improbable Planet, where he points out 4 additional factors in addition to M dwarfs not being supporting life. White dwarfs, red giants, hot stars, Cepheid variables, and binary star systems all have conditions that would prevent complex life. And you sort of shrink it down from 20% of the stars to 9% of the stars, have the right size, temperature, et cetera, to support complex life. Our solar system was born in a globular cluster with, this is a really interesting point. I don't know how to even start thinking about the math around this. But was born in a globular cluster with 4 concurrent supernovas, ejecting highly unusual amounts of heavy metals into the sun's gravitational well. Well, not only are we in a metal-rich solar system, we're in an unusually metal-rich solar system. I think it's aluminum is the one we have a lot of, and it turns out to be very important for various reasons. Followed by an exit outward, followed by stabilization of the outward trajectory just short of the co-rotation radius. That's the co-rotation radius is a point in the galaxy where the speed at which the stars are moving is equal to the period of orbit around the galactic center. And if you're too far from that in either direction, it would be fatal to life because the number of stellar encounters would go way up. And we're in this sort of Goldilocks zone of just short of the co-rotation radius. But the real amazing thing here is that you had to have 4 concurrent supernovas, which could only happen toward the center of the galaxy. Then the sun has got to move out, our star has got to move out to this safe place from the dangerous place it was, and then stop moving. This is another interesting point. A star with very little luminosity variance. In the book, Ross claims our sun has an extraordinarily low luminosity fluctuation. And he claims it is the least fluctuating star we know of. And that an average fluctuation would be fatal to life because of the temperature variations that would result in that. And then he makes another interesting and unique point, which is the orbit around the Milky Way of our star. We oscillate less in the vertical plane. We oscillate 228 light years up and down, whereas from the center, whereas an average star oscillates 400 light years. If you, he argues that if we went 400 light years from the galactic plane, we would be exposed to radiation extremes when we move above the disk or below the disk. And that would be fatal to life. So these are additional considerations. I could go back to the spreadsheet real fast because I also went ahead and put some of these in there. So here I have rare earth, which we did before, and now I add, and I don't really have a good basis for these numbers, but here they are. The orbit fluctuation above and below the galactic plane. If 2/3 of the stars have the average or greater orbit, it would be 33% have the average or less orbit. And the luminosity fluctuation above and below the habitable zone, exactly the same argument. If 2/3 fluctuate at the average or more, the luminosity, then, and this is one I would think I could find some data on, but I haven't been able to yet. You add these 2 factors in to the rare earth equation, and you get one. You get one civilization. Chuck, I know that won't be the conclusion you want to come to. But there it is.
But if we calculate there only can be one, and we know there is one, then 1 equals 1.
Yeah, that's right. And, it says we'll never have to answer those religious questions that we grappled with in the first meeting. I got just a couple of more points here, and then I think we're done. Yeah, okay. There's one other really interesting article I found. Abraham Loeb, who is a A-list celebrity when it comes to astronomers, Harvard astronomer. He wrote a recent paper, The Relative Likelihood for Life as a Function of Cosmic Time. So he takes a look at the lifetime of stars and their census, and this sort of a population analysis of the stars in the galaxy, and which stars have the right mass and temperature and all of that to have Earth mass planets in the habitable zones. And so this is a paper from 2016. He finds that life is most likely to exist near 100,000 stars 10 trillion years from now. And the low mass stars he's referring to there are the M dwarfs. 10 trillion years from now. Our conclusion, therefore, that the most conservative estimate put the probability of our existence before the current cosmic time at 0.1% at most. So if you remember the Fermi paradox, so one classical answer to it is we're the only one. Another classical answer to it is we're the first one. Then he goes on to say, however, the emergence of life may be sensitive to additional factors that were not included in our formulation, such as the existence of a moon to stabilize the climate on an Earth-like planet. Oh yeah, that's in the rare earth equation. The orbital structure of the host planetary systems, for example, nearby gas giants. Oh yeah, that's in the rare earth equation, or the rare earth book. The orbital eccentricity of the planets, that's in the rare earth equation. The effects of a binary star companion, Hugh Ross talks about that. The location of a planetary system within the host galaxy, that's in the rare earth equation. And the detailed properties of the host galaxies, galaxy type, metallicity of the galaxy. Galaxies can be metal poor too. That's in the rare earth equation. So while Bradley and Ward are being skewered by the atheistic science community that is offended by their conclusions, real scientists are supporting them, supporting their thesis at least. So that brings me then to the conclusion, all of which may explain the Fermi paradox, which is, if there's so many, the question is, if there's so many alien civilizations out there, why haven't they visited us? And the answer, well supported by the science, is they are not there. We are alone. And the Earth is amazingly special and anything but mediocre. And of course, with no aliens, there are no religious questions to answer. So with that, I'll throw it open to the group.
Thank you. That's a great presentation.
Yeah, I learned quite a bit. It was excellent.
Excellent. Thank you so much, David.
I had never heard of where the cells ingested but didn't process. That was all new.
Didn't digest. They ingested but didn't digest. Endosymbiosis. If you're looking for examples of miracles, the book, The Vital Question, is highly recommended. When there's this ATP cycle of producing energy where protons are actually pumped from inside the cell to outside the cell. The mechanisms are so intricate that you just look at it and say,
how did this happen?
This is too much. How could this happen? It's just too much. So I do recommend that book. It gets a bit dense at times, but
I thought the explanation for the evolution of the eukaryotic cells was interesting, that it happened once out of all those gazillion bacteria that have ever existed, and that it only happened once. I thought that's highly suspect, because first of all, it sounds like a miracle and you can't test for that. And,
right.
And the other thing was I guess I could use the word arrogance. They'll point to people and their personal beliefs as a reason to reject something, yet that bias does not apply to them. They have a bias towards a materialistic explanation for everything, but that's never in question.
Right. What is her first name? She wrote the book Lost in Mass. Hossenfelder is her last name. She's a well-known physicist. Has a very popular book called Lost in Math about how the search for modern physics has gone off the rails by becoming enamored with beautiful mathematical theories that don't have any hope for experimental support or evidence. And she has a really good YouTube series of physics. And in one of them, she's a guest along with Luke Barnes, who is a physicist who strongly supports fine tuning, the physical evidence for fine tuning. And the two of them and she's an atheist and he's a believer, and they're on this YouTube video, and she's describing why she's an atheist and he's describing why he thinks the evidence for fine tuning supports belief. But at one point in the video, she says, in her experience, scientists who are Christians keep their religion out of their work far more often and thoroughly than scientists who are atheists.
It's funny.
I'd like to ask a question, if I may. It says, if there are so many alien civilizations out there, why haven't they visited us? I think a common response would be that, well, they're declassifying all this government information. They're showing videos of these things and, Area 51. And they would say that there's plenty of evidence out there that we are being visited by extraplanetary people. I mean, how do you come back with something like that?
Yeah, that's a hard one. If you remember that survey from 2021 by the Gallup organization, 49% of Americans believe that UFOs are of alien origin. So you're describing a really common belief, I think. It's probably worthy of an entirely different presentation, but my own view is there's no evidence that they are. And you're trying to prove a negative, which is extremely difficult, proving a negative. I can't prove that, Mickey Mouse isn't hiding under your bed, but is invisible when you look for him. But you can set up a set of circumstances that make it unprovable. And UFOs are sort of there.
To come all this way and not leave a greeting card is pretty rude.
Yeah.
I think Hugh Ross even wrote a book called Little Green Men or something that I haven't read the book, but he posits that some of those sightings, the ones that cannot be explained by any other means, might be demonic in origin. I don't know. Has anybody read that?
I'm not.
Yes, I read.
I wrote a term paper in 1968 in high school on UFOs and what they might be. And my conclusions are still, I think, are still valid at the time, which is most of them are just mistakes. People don't know what they're looking at. It's lights in the sky. It's shapes in the sky. And there are no good photographs. Think about this. Every single human being carries a camera now. And there are no good photographs that show a mechanical vehicle that's a UFO. They're little dots that are, all of these films are little dots. I don't know if you guys know Josh Runyon. He runs Ratio Christi at UCSD, which is a student Christian group. Yes, and he was a jet fighter pilot for the Navy. And he has said that the films that show Navy pilots talking about them, they're not behaving like Navy pilots behave. The way fighter pilots behave if they want to engage or intercept is they go to afterburners and they go after it. And these guys never do that. He said they don't want to intercept them. They probably know what they are. And it's maybe a military vehicle. But that's a hard problem. The science behind interstellar flight is daunting. We didn't go into that here, but that was the third answer to the Fermi Paradox, is they're not here because it's too hard to get faster than, there is no faster than light travel. There's no basis in physics for it. And that if you are sublight, it's just interstellar travel is just not practical. Talking tens of thousands of years to make trips. So, you know, it's just from a technology viewpoint, you know, they aren't alien spacecraft. They're just not. But how do you convince a person? You can't convince a person who believes in conspiracy theories.
Yeah, it's true. It's like Bigfoot. Have you ever noticed how there is never a crystal clear picture of Bigfoot? They're always pixelated and blurry and.
Now, Bigfoot, I believe, is true.
So there's a wonderful National Geographic show on Bigfoot where they interview 4 people who have evidence of Bigfoot that's physical, hair samples or other things. And one of them, and then they do DNA analysis on the samples. And one of them was an experienced hunter who shot and killed a baby Bigfoot, shot at the mother and killed the baby. And he picked the baby up and carried it in his arms and put it in a place where he buried it. When he went back to get it, by the way, had been dug up by animals and was gone. But he held it in his hands and his arms, and he looked into its face, and he buried it. And he had a hair sample, and it turned out to be a bear. It was just a bear. But he wanted it to be Bigfoot so much that he didn't see what he was holding in his arms for what it was. And I think that's another thing we're dealing with here is people, you know, want there to be aliens because their lives are boring. And they sit in traffic and go to a job they hate. And then they go home and they watch Three's Company reruns on TV. And it would just be more fun. Life would be more fun if there were aliens. That's one explanation.
That's true. Any other questions or comment?
Well, thank you all for this opportunity. I've really enjoyed the group.